Okay, so in this particular problem, we're given a system of 4-point masses in a square arrangement, and then it asks us to calculate the moment of inertia of the system. So here, I'm just going to do a couple of axis rotation just to show you how to apply the function for moment of inertia. Okay, so once again, here's the square. The side of each length here is 0.5, and then you have 4 different point masses given here in the diagram. So hypothetically, what if the system rotates along this axis here, where it splits the system nicely in the center here? Okay, so if you can visualize 2 of these things spinning on each side, keep in mind that the masses are of different values though. Okay, so to find the moment of inertia relative to the axis rotation that I just presented on the slide here, you would just simply add up all the point masses relative to where they are and how far they are away from the axis rotation. So here, generically, you would just sum up all the point masses and then how far they are away from the axis rotation, hence Ri squared. So I'll just do it one by one, just kind of show you how to play with this function. Okay, so the first mass I want to do, I'm just going to go in a clockwise direction here, starting with the top left. Here's a 3 kilogram mass, and that length there in blue, that distance there, is half the length of square. The length of square here is given as 0.5, so half of 0.5 would be 0.25. So I'm just going to do it one at a time. So the first mass I have is 3 kilogram. How far is it away from the axis rotation? 0.25. And then don't forget to square the R value because that function here is being square. Okay. And then the second mass here is to the right, top right, which is 4 kilogram. Once again, this particular first problem here is pretty nice and symmetrical. The length there is also 0.25. So as you can see, you would just do like each term and then just use the distance away from the axis of rotation. Okay. And the third mass here to the bottom right, and that's 2 kilogram, and that is the same length away, which is another 0.25, and then we're going to square that. So as you can see here in my work, I'm just kind of doing each one at a time. And then last but not least, the 5 kilogram at the bottom left here is also the same length away. So for this symmetrical system, it's pretty straightforward. There's no trick traps here. Just do it 4 times and just sum up the value, and hopefully your calculator work is solid. Okay, and that, if you simplify my work, you should get about 0.875, and then the unit for moment of inertia is kilograms meters square. Okay, now I do want to point out, when you're given a symmetrical system, the short way to do it would just be add up all the masses in parentheses and then multiply by the value R squared. So in my work previously here, I have 0.25, 0.25, 0.25, 0.25. So that is a common term which you can just factor out. You don't have to, but it's less calculator work to punch in. So in my second step here, just to make a point, if you pay attention to symmetrical or symmetry here, you can just really do the same process. It would just be 3 plus 4 plus 2 plus 5, and then once again times it by the distance, and in this case the distances are all the same, so you can factor that out, and that'd be 0.25, and then you're just going to square that and it will give you the same answer. Okay, so however you want to do it. All right, now what if though you're given this particular diagram here, and then what if they shifted the axis rotation to be something like this, a diagonal through the 2 point masses as I have shown here? So what if it rotates like that? Okay, it's pretty easy. Again, just stick with the definition. You need the mass, and then you need the distance away from axis of rotation. So this one requires a little more thinking, not too bad. So here, I'm just going to start with the generic function here. The moment of inertia of the system is total masses that are far away from the axis of rotation times this value square here. All right, so the first one I want to do is I want to do the 3 kilogram. The 3 kilogram here is located at distance R with the axis of rotation here, which I have to find. I don't know what it is. So I'm just going to break this up into a right triangle. I'm just going to call that A square, and then going down here, that would be B square. And then once I know that, I can just do Pythagorean theorem, because this is a right triangle, and then I need to find what the length C is. Okay. Once again, the R value here is the distance from the point mass to the axis of rotation. So it's important that you don't make any false assumption. So here I need the length C. But I know what A is. A is just half of the length, which is 0.25, and B in this case would also be half because this is a square. So I'm just going to crack up Pythagorean theorem. C squared is equal to A squared plus B squared. A squared being half of the full length, which is 0.25, and likewise with B for this one because it is a square. And if you square both terms and then square root it, you will get that C is equal to 0.3536. Okay, so it tells us that the 3 kilogram mass here is 0.3536 meters away from the axis of rotation. All right, so that's the first term I want to do, the 3 kilogram on the top left there. and I'm going to times that Pythagorean theorem. I'm going to square that. Okay. Or if you pay attention, you really could just keep it as c squared here. Okay. Often kids would just kind of do c squared and then they'll square root it. But then hopefully if you pay attention to your work, you can actually just keep it as c squared, because down here r is square. So really you need c squared. So it would just be 0.125. So if you square root it and square it again, you get the same value. Okay, so it's up to you if you want to go in circles, but I did it here just to show you, just in case problems are not symmetrical, you can just do Pythagorean theorem and then use the value there. Okay. All right. The next point mass, that is the distance away from the axis of rotation, would be the 2 kilogram mass here on the bottom right. Well, this is symmetrical, so the length here would just also be 0.3536, but the mass here is 2 kilogram. So hence, for this one, I have 2 kilogram here times the distance away from the axis of rotation, which is 0.3536. I'll square that. And that's pretty much it for this one. Okay, if you simplify in your calculator, you get about 0.625. Once again, the unit for moment of inertia is kilogram meter square. But I do want to point out, as you can see, the 5 kilogram and the 4 kilogram does not contribute to the moment of inertia because the axis of rotation run right through it. So the R value would be square. So anytime you have the axis of rotation run through a point mass, that point mass contributes nothing to the axis, so excuse me, to the moment of inertia of the system. Okay, so while there are all 4 point masses here, there are only 2 point masses that contribute to the moment of inertia, which is 3 and 2, because they are a distance away from the axis of rotation. Okay, all right, I hope that helps. Stay nerdy, don't be whack.